In part C of this question, we're going to use the eigenvectors of the game matrix A to find a formula for the probability of being in any of the 4 states after n steps starting on node y. So to find the eigenvalues of this matrix, what we can do is we can actually find the eigenvalues of these two 2x2 matrices here. And the eigenvalues that we get from these two matrices will be the eigenvalues for matrix A. So let's start off with this matrix, which we'll call B, and we'll call this one I. So to find the eigenvalues, we're going to take the determinant of B minus lambda I. So that means we're subtracting lambda from the diagonals. That's going to be equal to 0. So to take the determinant, we're taking the product of the diagonal minus the product of the off diagonal. And if you work that out, it ends up being lambda squared minus 0.9 lambda plus 0.14. If you factor that, you end up with this. So solving this equation gives you 2 eigenvalues. You get an eigenvalue of 0.7 and an eigenvalue of 0.2. Now to get the other eigenvalues, we're going to do the same thing with this matrix here. So we're going to take the determinant of matrix I minus lambda I. So again, we're subtracting lambda from the diagonal. In this case, the off diagonal is going to multiply to be equal to 0, so I'm leaving it out. So we actually end up with 1 eigenvalue from this matrix. But because we actually have a quadratic here, we're going to end up with 2 eigenvectors from this 1 eigenvalue. Now we're going to take each of these eigenvalues and we're going to find the eigenvector of A. So let's start with our eigenvalue of 1. So we're going to take A minus lambda I, and our lambda is 1. So that means we're going to subtract 1 from all of the diagonal entries of A. So if you do that, you end up with this matrix. Now if we remember, the goal of finding an eigenvector is finding a linear combination of these columns that adds up to a 0 vector. And the numbers in the eigenvector are basically the coefficients of each column. So in this case, it's pretty clear which ones are the eigenvectors. We have a 0 column here and a 0 column here. So these are going to be our eigenvectors. So this eigenvector basically picks out this column, and this eigenvector basically picks out that column. Now we're going to do the same thing with our lambda of 0.7, our eigenvalue of 0.7. So we're going to subtract 0.7 from the diagonal of A. And if you do that, this is what we get. And again, a linear combination of all the columns that add up to a 0 vector will be this. It's a -2 there. So just to remind you, what this means is we're saying 3 times this column plus 3 times this column minus 4 times this column minus 2 times this column is equal to a 0 vector. Now do the same thing with our eigenvalue of 0.2. So we're subtracting 0.2 from all the diagonal. And the eigenvector for this eigenvalue is this. And now what we want to do is we want to set up an equation to express our starting point in terms of each of these eigenvectors. So our starting point is this because we're starting on node y. So we're going to have some part of our first eigenvector plus some part of our second eigenvector. Oops. That's a 1. And same thing for our other two eigenvectors. So some linear combination of these vectors here is going to give us our starting vector, which is our starting point on node y. So if you notice, this is really a set of 4 equations, so each row is an equation with 4 unknowns. So you can solve this, and if you work through it, you end up with a is equal to 7 over 12, b is equal to 5 over 12, c is equal to 2 over 15, and d is equal to negative 1 over 20. Now we want to know the probability of being on any of the 4 nodes after n steps if we start on node y. So what we're going to do is we're going to hit this vector and this side of the equation by an. This is where our eigenvalues are going to come in. So xn is a probability of being in any of the 4 states or any of the 4 nodes after n steps if we start on y. So that's equal to an times our starting vector, and n is the number of steps. Now we're going to sub in a, so that's 7 over 12, and our eigenvalue associated with that eigenvector to the power of n. Then sub in b times the eigenvalue associated with that eigenvector to the power of n. Now we're going to sub in c, and the eigenvalue for that eigenvector is 0.7. Now sub in d, which is negative 1 over 20, and the eigenvalue associated with that eigenvector. So you can actually just get rid of this 1 to the power of n in each of these terms because 1 to the power of any number is going to be 1. So you can just get rid of that. But what this equation is telling us is the probability of being in each of the 4 nodes after n steps if we started on y. So for example, if we take the top row, that top row is associated with node x. So that's going to be the probability of being on node x after n steps if we started on node y.